It's the massive amounts of data center infrastructure build out that's currently going on, and where that's being located and how that's changing the infrastructure deployment in the US, or solar panel growth or wind farm growth in different regions, also bringing about different changes to our physical world. And trillions of dollars across basically all verticals, all industries, is being invested as people try to make sense of this changing physical world and really anticipate what future changes might mean to their business, so they can optimize their own operations. Just taking a few examples, if you look at logistics and operations, right, they're clearly trying to optimize their supply chain, understand where people are moving, where new populations are being developed, new infrastructure is being developed, so they can optimize that last mile delivery to new buildings or new facilities that are being built. Or obviously in the risk and insurance space, with the changes being brought about by those climate disasters we just talked about, how can they better forecast their specific risk, build better risk models for flood, for fire, so that they can optimize their own businesses. And last but not least, forestry and agriculture, constantly trying to use different types of data, more telemetry, to understand the real situation on the ground for their specific crops, anticipate potential issues with their crops, or forecast their crop yield for this coming season, so they can again optimize their specific operations. Those are just a few examples. I think the good news is, though, that there's more and more data available constantly to help us all collectively understand what's going on in the physical world. Over 10,000 satellites currently in orbit around the Earth, and there seem to be new constellations going up every day with more frequent revisit rates, new types of sensors that are opening up new types of insights to the physical world. Then you have all the connected devices, so we understand better how people are moving, how people and things, including cars, are moving around the world, and all the data volume generated by those types of products. And also drones, the new drone capabilities really opening up new opportunities for aerial capture, and then the insights that you can gain from that high resolution imagery possible through drones today. So we're getting all this data, but it's traditionally been somewhat challenging to work with this data, and especially at larger scales. There are obviously legacy solutions, traditional geospatial solutions that have been built for some of these use cases, but typically perform well on a city level or a county level, but often can't scale to larger scales, continental United States or planetary scale type of solutions and insights that modern organizations need. Often that's simply because they're limited to work on a single node or have other physical constraints to their compute infrastructure. Then you have these the new class of more modern cloud engines, Snowflake, Databricks, and others, that people are using more and more for cloud native type of processing. But in terms of geospatial, they're often incomplete, right? Either incomplete functions, not supporting modern geospatial formats and data types, or not providing all the integrated operations that you want to do with this type of Earth observation data. And last but not least, the bar has still been pretty high. So you need deep expertise along the lines of Isaac's skills traditionally to build out workloads that can use AI and ML and apply it to these data sets. So working with PyTorch to build computer vision models that you can then train and work with against this data to generate these insights has traditionally been a high bar for people to get started with and working with this Earth observation data. But that's where Wherobots comes in. So we're trying to simplify all of those challenges with our spatial intelligence cloud. So Wherobots was founded by the creators of Apache Sedona, really focused on geospatial first and bringing speed, scale, and performance to these modern types of insights and workflows that people want to build. So we have a single integrated platform that provides you with out-of-the-box capabilities and productivity with vector data sets, raster data sets, or joining them all with your own tabular data sets. We're open core, so again, from the founders of Apache Sedona, so all the capabilities of Apache Sedona and compatibility with TorchGeo, where Isaac's a contributor, all built into the platform as well. And it's packaged up in a serverless and cloud native experience. So you can get started right away with our optimized cloud infrastructure without having to concern yourself with all the typical setup and optimization of the infrastructure for these types of pipelines. What that enables for your organization is really an elevated level of spatial intelligence. You might have your own business context, your own business understanding of your operations or your customers, and how they interact with your business. But now you can easily supplement that and join that, fuse that data together with ground truth information. That could be buildings, roads, other ground truth data about the physical world, mobility data, how vehicles, people are moving around in time in the physical space. And then these new types of aerial capture, whether that's satellite imagery, drone imagery, or aerial capture, all those data sets can be then fused together to give your organization a complete view that's relevant to your business. What happened, what could happen, predict and anticipate changes in the physical world. And all that's really made possible by the power of Wherobots, the fact that we can work with all these data sets, fuse them together 5 to 20 times faster than any similar engine out there in the market, really allows you to unleash these new insights and change radically how you use spatial data within your business. It's all done with a spatial data lakehouse architecture. So we work with your data in place. That could be S3 buckets you already own, cloud storage, or your own data lakes that you have. We can bring our compute to the data as it at rest and work with that data efficiently without needing to first ingest and fully index that data in a different environment. What that allows you to do is work with both legacy and modern cloud native data formats and bring this compute directly to that data. So within the Wherobots environment, you have discovery experiences. So you can find out data sets that we provide out of the box within our catalog or that have been shared within your organization. You then have the building blocks to build pipelines, dedicated pipelines that either work with those rasters or vector data or join data sets together, and tools to then automate those into repeatable jobs so you can use those consistently within your business operations. And the outputs that can be produced or published to a variety of different outputs depending on your needs. That could be a map data product that you're generating, or it could be layers that you then publish to your specific application and consume through Esri, Carto, Felt, or other visualization experiences. So that's a little bit about Wherobots and our spatial intelligence cloud. Today, we're going to focus in on RasterFlow, which is a new set of capabilities that we launched in December. We're currently in private preview. And here the focus is, just as we've simplified with Apache Sedona, making it easier for developers to work with spatial data sets and do that at scale with high performance, we're trying to do that same thing for raster imagery and the types of pipelines and processing that people typically want to do with satellite or aerial imagery. So we built a new ground-up engine from the ground up that's optimized for the types of processing you want to do with satellite and aerial imagery, and then being able to prepare that imagery for inference with computer vision models. As much as possible, we're trying to build in expertise within the platform so that you can lower the bar that we talked about earlier and reduce the skills that are required for people to start generating insights from satellite and aerial imagery. And we'll show you this in the demo, but you can get started with just a few lines of code. We've packaged in all the collective expertise of Isaac and our team and the collective industry into these pipelines so you can get started with RasterFlow right away. Whole business model is built on demand so that you only pay for what you use based on the scale and size of the workloads that you're executing. We're in private preview. We're finalizing our pricing. So stay tuned for more information on that shortly. But we're very excited about the efficiencies we're able to achieve here with this new compute engine. And we hope to be very attractive and disruptive in the market in terms of pricing. And last but not least, it's fully integrated with the rest of the Wherobots platform. So as you use these computer vision models to generate insights, for instance, extracting field boundaries or trying to detect sidewalks in urban infrastructure, you can instantly then use those results back within Apache Sedona and the rest of the Wherobots DB engine. So you can post-process those geometries to clean up the results of the model outputs, or you can join those data sets to use those within your business context. And we'll show you more about this upcoming in the demo. Just taking a look at RasterFlow at from the high-level architecture perspective, we have support for both data sets and models. So we have a combination of open data sets that we're providing out of the box that you can get started with right away. Today in the private preview, that includes Sentinel-2 and the NAPE data set for the United States, which provides high-resolution data for the continental United States. But you can also bring your own data to the platform. We have a process for bringing your own rasters. Today we support COGS. If you provide cloud-optimized geotiffs, you can provide an index into those and then start working with those data sets as well within RasterFlow. It's a similar story on the model side, where we have a set of curated open models coming from the Torch Geo community and contributors like Isaac and others that we're making available on the platform that you can get started with right away, but also a process for people to bring their own models. That could be open models from the broader community that are supported by PyTorch, or if you have your own fine-tuned models, you can bring those to the platform as well. And then within RasterFlow, you have these building blocks so that you can first ingest and prepare the raster imagery. That will include steps like ingestion, building composites, or building a virtual wall-to-wall mosaic. So you have a nice, clean input imagery that you can feed into our inference engine. So here, for example, just the screenshot shows we're building a NAPE mosaic. We're pulling in the necessary tiles required for NAPE for a specific AOI to generate a nice, clean virtual wall-to-wall mosaic that we can then use for efficient inferencing. This may also include, if you're working with Sentinel-2 or other data sets that might include cloud cover. In these building blocks, you have all the necessary tools to work with that cloud cover, discard it as needed, heuristics to help you get started right away and build a relatively cloud-free image that's a representative scene of that area that you can then feed into your specific model. That then brings us to our inference engine, where we've focused on efficient and parallel inference. So being able to run inference at scale, parallelizing as much as possible, but doing it in a way that doesn't introduce tiling effects. So we have a windowing operation here where we'll run your model across that virtual mosaic that we've just created in the previous step and do it in a way with overlap such that you get nice, clean output mosaics representing the predicted values based on your model that you can then use for further post-processing. So in this example, we're showing results from a specific model that's trying to find sidewalks and crosswalks, pedestrian infrastructure within urban environments. And you see predicted raster output values, predictions based on where it thinks those sidewalks and crosswalks are. At this point, it's in raster format, but we have built-in additional operators that you can use to vectorize that result, turn those predicted raster values, predicted output values in raster format into vectors. Those will give you initial geometries, in this case, representing the sidewalks. And then you can use the power of Wherobots DB to further post-process that. So here you see, for instance, a zoomed in example of specific sidewalks and crosswalks that were isolated on in a college campus environment. And we then used Wherobots DB to simplify those geometries because they're often jagged as outputs of the model. The geometries are often jagged in terms of pixel outputs. But you can use the built-in tools to simply create center lines or simplify those geometries such that you can get to ultimately a nice, clean, ultimately navigable path that you can use, for instance, for routing applications. All right, so that's a quick overview of the scope and building blocks we have within RasterFlow. We'll talk a little bit more about one specific model that we're going to talk about in demo today. So Isaac and others in the Wherobots team have been working on a model called Fields of the World. This is sponsored by the Taylor Geospatial Engine. They're trying to help produce a global model that can be used to find field boundaries based on Sentinel-2 data around the world. This model recently was published, a new version of this model, version 2, was recently published and released. And this model basically takes in Sentinel-2 data and then predicts fields, what's a field boundary, or what's not a field, based on those inputs. And once you have these clean field boundaries for any part of the world, it enables additional types of crop intelligence. So if I know these are different field boundaries, I can start to isolate, well, this field is of this type crop, this field is of a different type of crop, and I can start to do more accurate crop analysis or yield predictions based on those crops by field boundary. And there's a blog post back in December that Isaac authored here that talks about our work with the tailored geospatial engine. The fact that they could run this model as they were finalizing version 2, the fact that they could run this model at global scale allowed them to see where it was working well and where they still had areas for improvement. So we did a continental United States run for tailored geospatial engine. We did other selective countries here, Japan, Mexico, at very low cost. And we're actually gearing up to do a worldwide run for them. Now that they've finalized this version 2 of the model, we're going to generate outputs for the entire world, and together with tailored geospatial engine, publish that back out to the open source community. Let's just dive in a little bit more detail about how this works in practice, how we run a model like Fields of the World with RasterFlow. So in this case, we'll show you this in the demo. We have what's called a recipe that stitches together all the building blocks for this specific flow or this specific workflow into a high-level recipe that you can call with just a few lines of code. And what that recipe does is it first sources Sentinel-2 imagery. We know that we need to use Sentinel-2 as input for this specific model. And more specifically, this model requires two basically inputs. It needs a representative scene of what that area of interest looks like during planting season and what it looks like during harvest season. So we have built-in building blocks to build both of those scenes and then combine them into a single mosaic. And that already includes processing or pre-processing like removing cloud cover. So you get an averaging over a time range so that you get a nice, clean, representative scene of what that area looks like during planting and harvest season. We combine that together, all that together into inputs that we then feed into the Fields of the World model. Run that at scale, distribute it as needed to run efficiently across your chosen AOI. And the output of that model then will be in the form of rasters. There's another raster output that has predictions for those different classes. So confidence levels for each pixel. Is this a field? Is this a field boundary? Or is this not a field at all? Once you have that, you can visualize that, inspect that, see how the model's performing, confirm that it's working as expected, and then you would maybe go through another subsequent step to vectorize those. So that's just one more step you can do to vectorize those outputs based on those prediction values, create geometries that are in the form of polygons. And you see them here in tabular format, but you can also work with those geometries as standard spatial geometries within Wherobots DB. At that point, you might want to do some refinement and post-processing on those geometries. But once you have nice, clean field geometries, you can use the power of Wherobots DB to then do that crop level intelligence or field level intelligence. I can join it with crop indices representing things like NDVI. This is what Pranav will show you further in the demo, how you can take some of these raster flow outputs and then make use of them within Wherobots. And just to cover quickly, beyond running computer vision models against raster data, we also have other capabilities within Wherobots to work with rasters. So we have what we call OutDB raster support. That allows you to point to rasters or use our stack reader to read in rasters that are sitting maybe in S3 or another cloud system, and then work with those within Spark without having to ingest all of those rasters. So you can create this OutDB raster, a Spark data frame, that you can then apply different operations to and do that in an efficient, distributed way while working with minimizing the data transfer for these large raster data sets. So we have built-in functions to do raster algebra, for instance, to calculate indices like NVDI, or do resampling or CRS reprojection at scale. Those are all built-in functions that use the power of Sedona, that use the power of Wherobots DB and the power of Apache Spark to do those at scale in a distributed compute environment. And then we also have built-in interoperability between rasters and vectors. So if you have an area of interest represented by a vector, you can do zonal stats. You can take that boundary and compute zonal statistics on your raster. You might have like rasters that represent elevation, a DEM model that represent the elevation of a specific area, and you could quickly get averages or other statistics on that area based on the geometry that you're joining with those rasters. And then other built-in functions to work with those rasters based on different clipping, masking operations you might want to do. And last but not least, you also want to talk about our new MCP server that's currently in public preview. So for those of you who haven't heard, MCP is really a standard protocol that's emerged, allowing LLMs and agents to have a standard way to talk to cloud systems or any remote system, basically discover what's available and learn about the tools that are exposed, in this case, exposed by Wherobots, so that you as a user through the LLM or agent can be more productive and can use natural language to interact with tools that are exposed, for instance, by Wherobots. So our public preview of our MCP server allows you to work within VS Code or your other preferred IDE. You would configure our MCP server, and then you can just start asking questions in natural language against both the data sets that are available within Wherobots and also use the types of functions that we have built in to do geospatial processing. Pranav will walk you through a demo here, how this facilitates more advanced analysis with some of the outputs that we're going to generate through RasterFlow. We also have tools now then within MCP. Once you get to a level of analysis that you're happy with, you built out a pipeline with the help of MCP and your LLM or agent to do that. It's also a very straightforward step to then just simply convert that to a notebook or a job that you can run on a repeated basis. Really take that initial ideation that you're doing together with the LLM and agent and then turn it into a production pipeline. All right, with that overview, we're going to switch over to the demo. Jump over here. All right, so we'll do a quick walkthrough of our Wherobots cloud environment to start. So here we're showing our notebook environment. This is where you can spin up our hosted Jupyter environments, different compute sizes available, CPU and GPU variants, depending on what you're trying to do, that you can launch directly from within Wherobots. We'll come back to this in a second as we walk through a specific notebook. We also then have our data hub. This is a combination of data that we provide out of the box that you can get started with right away. So we talked about data of the physical world, Overture maps, building footprints, roads. We have data from Foursquare for how people are visiting different retail establishments, OSM, New York City Taxi, a large set of data sets you can get started with right away, or iceberg catalogs that you create yourself within your organization. So any data that you can store and share with others in the organization is also populated here in the data hub. Then we have our model hub. This is specific to RasterFlow right now, and it shows the 4 initial models that we support in the private preview. You get a brief overview of the different models. So this one, for instance, predicts canopy height, the height of the canopy based on aerial imagery. We also have models for road detection or sidewalk detection that we talked about earlier, and the Fields of the World model that we're going to use here in the demo. Each of these models also has an associated solution notebook, standard notebook that just walks you through the process of running that model and then working with those outputs within Wherobots DB. Yeah, and not last but not least, you have storage. So we have our standard managed storage environment where we provide S3 capabilities for you out of the box, but you can also create your own storage integration. So if you have your own cloud storage, your own S3 buckets that you want to work with the rest of the Wherobots DB engine, that's a simple, straightforward process to just simply attach that storage to Wherobots, and then you can start processing that data with our engine. All right, that gives you a brief overview. Let's switch over to a specific notebook. This is the notebook that demonstrates how to run the Fields of the World model with RasterFlow. So a couple things to point out here. I'm just going to show you how easy it is to get started. Again, this is our highest level API that we call recipes that are pre-configured workflows simplified to allow you to get started right away with these types of models. There are also lower level interfaces that we support. So you can do the individual building blocks and have specific controls if needed. But at this highest level, all that's really required is an area of interest. So here we're using the WKLS, or well-known location service package, to specify an admin boundary. I want to run this over a specific area in Kansas. So I'm using this function to basically get the admin boundary for Haskell County in Kansas, and creating that as a GeoJSON that they then specify as my AOI path. I then initialize the RasterFlow client, kick that off. And then running the model is as simple as this one function call here. So I'm going to call this build and predict mosaic recipe. I'm going to specify the AOI I configured up above. I specify the time range, so the start and end dates for that I want to use to build those mosaics specifically for fields of the world. If I want to reproject the outputs, you have an option to define that CRS here. And then otherwise, it's just a matter of specifying the specific model. So we have these built-in model recipes for any of the out-of-the-box models that we have. In this case, I'm going to run it for fields of the world. And that's it. I kick this off. That kicks off a workflow to then do all of those steps we showed in the previous diagram, source the imagery for Sentinel-2 from a specific S3 bucket, build those mosaics, feed those as input to a model, and generate the raster outputs. In this specific case, I had run this multiple times, so the results were already cached, and I get the results back immediately. Otherwise, the time will vary based on if you're running this for the first time, the time will vary obviously based on the size of the AOI that you're trying to cover and the complexity of your model and the density or the resolution of the imagery you're using. But at this point, I now have model outputs. So this is in ZAR format. We're using ZAR internally to represent all the mosaics and the outputs from our models because of the efficiencies it brings. And then we show you within this notebook how you can do some initial visual inspection of those model outputs. Again, this will be a large raster file, so we're not going to be able to visualize the data set entirely. But with a few lines of code here, we can use standard tools like hvplot to do a quick visual inspection of a smaller part of that AOI, just to make sure the model's working, we're getting those predicted field boundaries. And if you see here, we get some initial results that look pretty decent. At that point, if we're happy with the results, we can go further and go ahead and vectorize those. So that's just one more step, essentially, to vectorize that mosaic. We're going to take those outputs that we just generated. We're going to specify which of the classes, the predicted classes we really care about. So we're just going to discard the non-field background. We don't need to vectorize anything that was determined to be non-field. We're going to vectorize the others. And that's just one more flow. So that kicks off another process to then generate outputs or vectorized outputs. These are then in GeoParquet format. So once we have these GeoParquet outputs, we can spin up our Sedona Spark environment within Wherobots DB. And I'm going to create a database. I'm going to basically create an iceberg catalog, and I'm going to store those GeoParquet results directly into our iceberg catalog so that you can share those with others in the organization. And that's just a few lines of Sedona SQL here to create the database, read in that GeoParquet, and then write it out to a specific table I configured here. And at that point, we've gone all the way from running a model, vectorizing the outputs in a GeoParquet, and then we're able to store those directly in Iceberg. There are a few more steps to show further options, like visualizing those results, either in tabular form or, in this case, using Sedona Kepler to show the vectorized outputs and visualization of those. We also have our built-in distributed PM tile generation capability. So if you're generating large-scale vectors and you want to output those in PM tile format, that's just another few lines of code to take those vector outputs, generate PM tiles. Here I'm running it essentially with no options, but you have full control of controlling what's visualized at different zoom levels if you want. But otherwise, it's just a single line of code to generate those PM tiles and then show those as well within the notebook. One more thing I'll show before turning it over to Now I'm just going to show some larger scale visualizations. So there we were working within the notebook, and again, we're trying to work with a small set of that raster data so that we can visualize those locally. But here we're working with a partner of ours called EarthScale that enables large-scale visualization of rasters. And here we see the run we did to predict field boundaries for the entire continental United States. This is, again, large raster data set covering the whole continental United States for those field. In this case, I'm specifically visualizing the field boundaries. And we can zoom in and interact with this at scale, and you start to see some of the predicted crop boundaries here in the middle of the United States. Yeah, that gives you a sense of the type of scale and efficient that we can operate on, and what that then enables. Now that you can run models at scale, at this type of scale, previously was simply not feasible from a cost or complexity perspective. We're hoping that really unlocks new use cases for, as it did for Fields of the World, but hopefully for your organization as well. All right. With that, I'm going to turn it over to Pranav to show you how you can then work with some of these outputs further with the power of MCP.
Thanks, Phil. Let me share my desktop. Cool. Awesome. I'd like to now briefly show you how the Wherobots MCP can be used to move from a high-level analytical question to a production-ready geospatial application in Wherobots. And what I'd like you to take away from this is that the MCP server itself is not the new thing here, but as you know, geospatial processing usually requires special care because of large data volumes, specialized data types, different formats, and obviously compute bottlenecks. And Wherobots is able to handle that spatial complexity under the hood, and the MCP server, together with the LLM of your choice, in this case, I'm using Cloud Opus 4.5. They're able to take full advantage of that to support iterative and end-to-end analysis on geospatial data. So to keep things moving, I'm going to walk through a 25-minute conversation I previously had with the Claude model, which is connected to the Wherobots MCP server in my Visual Studio Code environment. The focus of this conversation was to analyze how crop health changed between 2020 and 2021 at the agricultural field geometries level that were produced by the RasterFlow using the Fields of the World model. So at the start, I don't know what data exists in my Wherobots environment, which catalogs are there, what tables exist, or what's relevant to crop health. So the first thing I do here is to simply ask the MCP to look at what data exists in my Wherobots catalog, and I'm not making any assumptions. I'm not guessing table names. It's just exploring. So yeah, this is the response that it gives me. It lists out a bunch of different data sets by just reading the metadata of all the tables I have in my Wherobots account, and gives me all the relevant data that I might use for an analysis like this. So what's powerful here is the MCP is giving me a landscape. It's given me multiple data sets, not just one, and different sources. This already removes a lot of friction for me because maybe I'm new to the data team and I didn't have to go through the entire catalog to find out what's relevant. I'm able to do that simply with one query. So now, even though the MCP has surfaced the NDVI dataset as the most relevant, I don't actually know what NDVI is. Maybe I'm a regular data analyst who doesn't deeply understand geospatial data yet. So I don't know what NDVI is or how it's derived, but I do know about European Space Agency. So here in my next prompt, I'm asking to explain the meaning of NDVI. And it does that. It explains the actual meaning of NDVI and how the ESA actually produces it from satellite imagery and why it's a good proxy for crop health analysis or vegetative health. I'm still not running any code. I'm just building confidence in my understanding of these different concepts that are involved. Now that I understand the data conceptually, I'm ready to narrow down. I picked data sets that I'd like to use, the NDVI rasters from 2020 and 2021, and the agricultural field boundaries detected by RasterFlow. These field boundaries cover the Central Valley region just above Sacramento in California. Yeah. So at this point, I still don't know how the analysis should be implemented. I'm not thinking about joins or like raster data and geospatial functions at all. All I do is describe what outcome I'd like to get, and the MCP is able to infer correctly, like the spatial analysis from that intent that I specify in my prompt. Yeah, so here it just walks me through the exact query it's going to be running, uh, how the SQL is going to be structured, like the CT, and the final select statement is going to give me some aggregation about the health change between the 2 years. Um, yeah, at this point, I'm comfortable with the approach, so I give MCP the green light to run the actual analysis. Yeah, this is where we kind of cross the exploration into real computation. Uh, and something kind of realistic happens. The query times out. The MCP points out that uh, you know geospatial analysis often requires spatial indexing, join strategies, and things like that. So it times out in 15 minutes. But I do know for a fact that Wherobots is able to do all that handling under the hood, and you shouldn't be worrying about very special care about geospatial data itself. So I ask it to, disregard any considerations about spatial indexing and don't try to optimize, just run a simple join, and that should be fine. And then it iterates through a few queries. It also fixes the RS zonal stats function, and it's able to give me a consolidated summary of the analysis for just 100 rows of fields, just to give me a brief look into how the analysis output would even look like before I actually decide to scale it further. So I'm happy with the result here. It has given me a bunch of NDVI specific statistics. And here's the cool part. Like here, I ask it to, translate this exact same workflow into a Wherobots job that runs on the entire area of interest, not just 100 rows of data. Here we have iterated through the analysis and like confirmed the results look good. So I'm happy with that. And I've asked it to create a job that does that at scale and then saves it out to an iceberg table uh, in my catalog. So it goes ahead and gives me this .py file, which is going to enrich my fields of the world geometries with the NDVI statistics year over year between 2020 and 2021. So what's important here is that this .py file is after iterating through the analysis at a smaller scale, and the MCP has created the exact job that is going to perfectly work in the Wherobots cloud environment. So I'm able to trigger the run from Visual Studio Code itself and monitor how the job fared look at details about it, like how many spatial units it consumed, the logs, things like that, that I might be interested in knowing just from a cost perspective as well. So this particular run, it took about 52 minutes. Yeah. And then after producing this iceberg table, I'm able to feed that to, application layer like Felt, for example, to visualize this data and to see how these NDVI results look like at the field level. So here is that visualization, and I'm able to really deeply understand the crop health across a certain region via this visualization. I'd like to briefly show you the complexity of this entire workflow and things that I, as a general data analyst, didn't have to worry about. Obviously, the spatial indexing, partitioning, the join strategies, I didn't really have to worry about. But just to show you the scale at which this performed, in my data hub, I see that the fields of the world data has about 16,000 vector geometries from all the fields of varying sizes. And the NDVI that we conflated and generated the zonal statistics from, that data is here in my own catalog. And it has about 19,000 or so rasters. So does the 2021 data have about 20K rasters. And all these rasters are the out-DB raster formats. So these are references to the actual physical rasters that have been stored on the ESA public S3 bucket. So these have not been pulled into the Wherobots environment. Only the relevant pixels get pulled in when running zonal stats on them. So this makes performing joins between rasters and vectors extremely efficient, and then running zonal stats as well. So this entire workflow running in about 52 minutes on a medium-sized cluster is pretty phenomenal to me. Yeah, that's all I have to show here. Thank you.
All right. Well, thanks for going through all of the different demos, the functionality. It's really cool to kind of see it in action and understand some of the scale and all the different pieces there. I wanted to just kind of open it up for questions and kind of get a sense of, you can post those again in the Q&A, or you can use the comments tab depending on where you're watching this. But I just kind of wanted to start with a few, key points here, which is like, understanding how this worked. We talked a little bit about the fields of the world model, how that fit in. Obviously, that's a existing sort of model and things like that. How did that kind of all come together? How are you able to bring that model into the system and kind of make it work? Where it was obviously running somewhere else before, but now within RasterFlow, how are you able to like make that just kind of seamless and integrate it from that perspective? And then what does that kind of showcase in terms of, the different steps to make that a reality? Obviously, we're talking about temporal time slices. We're talking about, imagery that may or may not need, correction or cloud cover and all these different pieces, the mosaicing. There's a lot of different layers there. So let's just kind of dive into that process and kind of open it up a little bit to talk about that. And then I have a few other questions we can talk here. And then as people have questions, I'll go ahead and start to add those in here. But yeah, anyone want to be the volunteer and pick up that first topic?
Yeah, I can start, and then Isaac, would love you to chime in as well. But yeah, it feels the world. So essentially, we do have this process for bringing your own model to the platform, and we use that same process to onboard the models that we provide out of the box, including fields of the world. So today we support PyTorch models that have been exported in a PT2 archive format. we have a new solution notebook that's now included in the product. If you run RasterFlow, you'll see there's a notebook that will walk you through the steps to take any model and any PyTorch model and walk you through the steps to create that archive format, and then configure it in a way that it can be used within RasterFlow. So that was the work to initially onboard the model. We also then, we provided this high-level recipe that stitches together those building blocks just so you have a simplified way to try that model out with that one line of code. But otherwise, once you onboard a model, if you were to onboard your own model, that's not Fields of the World, you could do that same process, export it, register with the platform, and then use those lower level building blocks. I want to first build a mosaic because I need imagery from Nate as input to my model, for instance. And then, okay, now that I have that mosaic, let's run the model that I just configured and generate those output results.
Yeah, no, I think what's cool is to, there's a level of just simplicity in terms of bringing on an existing model, bringing that into the system and having it run, and then obviously connecting to the data, handling that whole process there. If what's like a good like before or after, kind of like what would this process look like if you were doing this without RasterFlow? What does it look like, now? Can you kind of like, break that open a little bit to say like, okay, here's what we might have been having to do before, and here's some of the things that, we can do now that help make that a little more scalable and things like that.
Sure. Yeah. I think, to date, there are platforms where people can do this today. At least certain parts of this, like Google Earth Engine is probably the closest analogy, where you can take imagery data sets that they pre-ingested, work with them, and then you have to connect it with Vertex AI if you wanted to run a computer vision model against those data. But we're much more open, right? Google Earth Engine are really limited to the data sets that are pre-built into Google Earth Engine. It's very challenging, if not impossible, to bring your own data sets to work with within that platform. You do have to connect with Vertex AI, connect with BigQuery if you want to do all the types of analysis we just showed with that end-to-end demo. And hopefully we're able to share shortly as we come out of private preview some of the price and performance advantages that we specifically have over Google Earth Engine as well. So stay tuned for more on that front. So that is one option. Otherwise, people are often doing this themselves and doing all the work to stitch together their own pipelines to source the imagery, do that pre-processing, build the mosaic, handle cloud cover, then feed it to an inference engine. Oh, realizing that if I just do it tile by tile, I get these tiling effects. Wait, I need to do something different. So, it has been done, and people often build those pipelines themselves, but it requires a high level of skill to build those pipelines and significant costs that may reduce also your time to market for actually generating these insights.
Yeah, no, that's great. How would you kind of compare it to like, Earth Engine and some of the, how things have previously run there? I mean, Earth Engine's been around for a long time, has a ton of data in it. You can do quite a bit with it. But like, what are the main differences if people are kind of asking that question? Is like, okay, how does RasterFlow compare to Earth Engine, and what are the things that either one does differently or can do it versus can't, things like that?
Yeah, I think that the main ones I would touch upon is we're more open. We're built around open formats, cloud native data types that you can work with directly where they already sit. You're not only limited to the data sets that are available within Google Earth Engine is one. We built out this platform from the ground up. Google Earth Engine is a bit dated at this point, so we think we have real efficiency gains with the new platform we've developed. And that will ultimately manifest itself as a much more price competitive product that, again, I hope to share more with you all in the coming weeks as we exit private preview about how we'll compete on price with and performance with Google Earth Engine.
Awesome. Yeah, great. There's a few questions here. One from Tim. Can you use this to gather and work with data for real estate purposes, demographics, things like that? What are some of the use cases that you could potentially use this for?
Yeah, definitely. We're talking actively to a number of our existing customers that are already using our existing capabilities for helping to build insights and products, map products, or data products around real estate, um, or parcel data, those types of use cases. And now they're trying to augment with additional insights by using raster imagery. High resolution raster imagery, can we extract finer grain details from buildings, like how many buildings have solar panels, or those types of details to further enrich the insights they might already have of the data products they're generating.
Yeah, awesome. And then the question from Linda was talking about the compute infrastructure that the inference process runs on. Kind of understanding what's happening behind the scenes there.
Right.
You can read the full question there, but yeah, just kind of describing how that computes and all the different pieces there, and then how does that kind of fit in with the bigger picture of Wherobots Cloud and things like that.
Yeah, great question. Yeah. So in my specific demo, there were basically two or three parts, right? We first kicked off that recipe to do all the ingestion and preparation of the data for model inference. That's using the RasterFlow engine, which is based around Ray. We're leveraging Ray and love Ray for its ability to run compute efficiently and distributed pipelines for this type of work. And then the results of that were then ultimately, after the second step of vectorizing, those were GeoParquet that, as you mentioned, we then brought into the Spark environment to work with them with the power of Wherobots DB, Apache Sedona, and all the existing great tools we have in the Spark world to work with vector geometries as well.
Awesome. Yeah, and then I think one thing that's cool is, like, there's obviously a bunch of models that we've brought in, so people can start running those. Obviously, you mentioned the solutions notebook, so anyone can kind of go in. You sign up for a Wherobots Cloud account and start working with some of those. But the one that's really interesting, I think, is like the ability to bring your own model. Like, what does that look like? And then what does that kind of, can you talk about where you plan on taking this in terms of the future beyond some of the models you have, how people can kind of start bringing their own, and then what are some of the next things that you're really looking forward to from RasterFlow?
Right. Yeah. Yeah. We think too, that's really where this gets really unlocked. So we're providing a set of curated models to people to get started, get experience with the product. But really, I think as people look towards real operational production use cases, it's likely going to revolve around them bringing their own model, or maybe with a partner's help, to have a model that's specifically tuned to the insights they're trying to extract. So today we're starting with a process where you'll have a solution notebook that walks you through all the steps. It's pretty much, if you're familiar with PyTorch and you've done work with PyTorch before, it should be a standard process. So you create this specific export in PT2 format, then you can work with that model in RasterFlow, either by storing it in Hugging Face or in S3, and we can pick it up from there. But that's just the start. We have much bigger plans here as well. So today it's really bring your own model for someone who knows PyTorch and someone who's familiar with that framework. We're going to try and further lower the bar here going forward to truly help them simplify the process for taking any open source model that might be out there, and as much as possible simplify that onboarding process so that others can make use of the wide variety of models that are out there in TorchGeo and other communities.
Great. Well, yeah, we're right at the top of the hour here, so I want to there's one other question here. Sorry, last one, just as I was about to sign off, on gridded formats, things like that, or is it mostly target imagery? No, Linda, no worries, you're all good. Yeah, last question here, right before the buzzer. So, anyone want to take that one?
Yeah, so we do consider non-imagery. We already are able to build time series, and because R is n-dimensional, it's very similar to ingesting the netcdf type format data like climate and weather as well. So yeah, that we don't have. I don't think we have a tutorial for that, but that's definitely like coming up in the next couple weeks. Earth embeddings is another big one that we are currently adding support for. Yeah, I would love to have
Cool.
you as a beta tester.
Yeah, Awesome. Well, that was the last thing I was going to leave it with is, if you're interested in trying this out, testing it, feel free to get in touch with us. You can sign up for a Wherobots account, get in touch with us there. You can reach out to any of us on LinkedIn. This whole thing has been kind of streaming on LinkedIn. So if you want to add a comment there, or you want to shoot us an email, you can send that over to support@wherobots.com, and we will be sure to get in touch with you. So yeah, there's a last slide here. You can check that out here. The URL's there. So we got a lot of ways to get in touch with us. So we're hard to miss. So feel free to reach out. We'd love to have you try out RasterFlow. We'd love to hear your feedback. Go ahead and jump into the preview there. And yeah, that's it for today. So if there's any other questions that follow up, just please get in touch. And yeah, Pranav, Phil, Isaac, thanks for joining me here today. I'm excited to see more people try out some of these new tools. And yeah, we'll see you